welcome everybody to Weather Watch. I'm Pete Pokran. I'm the computer systems admin for AOS, and probably most of you know me. Anyways, Michael's not here today, and so Zoe and Professor Tripoli and Ian Beckley are going to be showing some stuff, and if you have anything you want to share, I'm going to keep it pretty loose, and we're going to be starting with Professor Tripoli as soon as he's ready. So.
Okay. Well, I thought I'd start by talking about the global jet stream patterns again, and whether they're anomalous or not. And as you've seen before, I like to look at the jet streams in terms of 40 meter per second contour or 40 meter per second surface, and then I shade it by potential vorticity, the magnitude of potential vorticity. So the colorful regions are low potential vorticity, and then these are all 40 meter per second contours below about 25 kilometers above the ground. And this is the 29th of October, which is today, but 2016. So I've done it now. I've done this for 6 years that we've been running this. Actually, we've been doing it for 8 years, but the first 2 years are a little different, so it's hard to put them together. But I'm just doing it for the last, for here, I'm just going to do it for the last 6 years. And these are the jet stream patterns on this day in 2016. And you can see that this jet stream to the south, which has a little bug in the code that spews it toward the pole here. But if you just look at the gist of it here, the southern jet stream is the polar night jet that's left over. This is 29th of October again. And when you look at it from the side, you can see that the polar night jet is up very high. And then the other jet streams over here, further to the north, which are subtropical jets, are much lower. They tend to be around 25 kilometers. You can see that here. And you see that when you look down inside the polar night jet, you can see these subtropical jets kind of enter into it and affect it. And so this is something that happens all the time. If I look at it from the side, I can kind of see that connection a little better. But in the northern hemisphere, there's no polar night jet yet. So I was thinking last week that this year was pretty unusual that there wasn't a polar night jet, but maybe not, because there's not really one there. Now, if you look at the speeds, if you take it down a notch, instead of looking at 40, look at like about 30 meters per second here, then you can see a little more evidence of the polar night jet in the northern hemisphere. So it's there, it's just not there at that level. Let's just look at 30 meters per second from now and go forward.
So this is the same day, but 6 different years.
That's right. This is 29th of October, excuse me. Sorry, here. This is in 16, so there's hardly any polar night jet in the northern hemisphere. 17, there's the polar night jet trying to form in the, but there's still one in the southern hemisphere yet. And here's 18, 19, 2019, still polar night jet. 2020, last year, strong polar night jet here, much more robust. And a little hint of one there. Where's my, I did this before me before.
We didn't get data this morning, so you don't
No,
have...
this is from 0Z, right?
12Z.
Oh, I got the 12Z. That's my problem. Let me start this over again. I did another. I picked up the wrong. Yeah, that's the one that had the holes that I decided not to use, and then brought it, I turned it on anyway. Here's, this one will be better. I'm going to choose my pixels so I use more of the screen. I have to get my contour intervals. Meters per second. And I want to shade it with potential vorticity at the level of maximum speed. Okay, so that looks like what we had. Okay, now step through it. 16th, 17th, or 2017, 2018. 2019, a weaker polar jet in the southern hemisphere, a little bit up in the northern hemisphere, and 20. And there's 21, but it's not there again. I don't know why.
So it's 12C.
Yeah, you're on 12 zero.
Close it. Didn't I just put up the...
You put up the most recent one, but it was from this morning.
This is 0Z or the file name.
Yeah, it says 0 Z, but
It's not. That looks like what it should be, but I don't understand why it's saying 12Z. I got the wrong ones. Okay, well, we can use the 12Z then, that'll work. So, yeah, it's not optimal, but we'll need to do it. All these data things are really doing me in. So here's the jet streams. I won't put on the potential vorticity in interest of time. And step through them. This is 12Z this morning, and we have the big polar night jet. One thing I wanted to show here that I thought was interesting is to look at the ozone. It's associated with that. And we have that. It's an analysis on the GFS. Here it is. There's a contour analysis of the ozone, what it normally looked like at this time of the year. And this is at low levels. Let me turn off the speed for a minute. So we just see the ozone now. This is the ozone here at 12.3 kilometers, and so I can go up in elevation. See it increases. It's increasing at 18, 19, 20. And if I get all the way up to where I have the top of my plot here, this would be at 24.5 kilometers. We can see this very, very low ozone at the southern hemisphere, near the South Pole, which is associated with the so-called ozone hole this southern spring. And at the same time, we are developing an ozone anomaly up here in the northern hemisphere, but it's a wave number 1 effect. It's not really at the pole. It's shifted a little bit to the south over Asia.
Can we put a map on that? Yeah, there it
So you can see the map. So this ozone minimum that's developing now in the northern hemisphere is over Asia, and the southern one is down here. Now this is interesting that it's an anomaly. If I go back to the beginning, you could see that the southern ozone minimum, which would normally still be there at this time of the year, is not quite as strong if you go back to 2016. And if I step forward to 17, it's not really low. It's maybe a lot lower in the northern hemisphere now. And 2018, northern hemisphere doesn't have much at all going yet for some reason. Southern hemisphere is pretty low again, but not as low as it is now. In 2019, we already had a very strong minimum in the northern hemisphere on 29th of October, and the southern hemisphere was pretty much wiped out with the ozone minimum. And then again, if we go to 20, it's low, and again 21 is ridiculously low. So this is an anomalous year with the southern hemisphere ozone hole. So I just thought I'd point that out. I think that has something to do with the particularly strong jet stream that's going on right now. Let me turn this off to see the jet stream. Another thing that we can do, I had this all set up and then I lost it right before I came here, so I'm sorry about that. I have to put a new variable in here for speed at the same time. What I want to do is look at the speed at minus 15 meters per second. So this is easterly wind, the jet for easterly wind here. And I will color this with the potential vorticity again. And I need to use my script, and I'm probably going to get in trouble and it's going to kill it. It would have been so nice if I could have just saved what I was trying to do before I came. Okay, here's the potential vorticity with the easterly wind. And what's interesting about this here is the easterly flow, if you just look at it alone, is very, very strong right across the equator, right on the equator. And you can see that's up very high. It begins around 20 kilometers and it goes up through the top of this plot. And this is the Quasi-Biennial Oscillation. So if we look at this from the beginning, if I just animate through it real quick, you can see it flashes on and off. And that's because this changes every year. This is 2016, which was an even year. And in the even years, we tend to have a westerly anomaly at the equator, and so you don't see the easterly anomaly. Go to the next year, 2017, it's an easterly wind at the equator. 2018, this was a funny year actually in QBO, but there was a little bit of, at least of a QBO left over in 18. But then 19, an easterly wind left over. 19, it flipped back to a more westerly or a very weak easterly flow. If I change the contour interval here, there were some anomalies which were said to be unprecedented around this time in terms of the regularity of the oscillation. Going at minus 15, if I relax an interval about minus 9, you can see you can see the easterly anomaly still along the equator here. But it's much weaker in this year than it has been in the past. Then you go up to 2020, you don't see the easterly anomaly anymore. In fact, there's some westerly winds in there. On the westerly QBO, it's a little harder to look at because there's a general easterly pattern in the tropics overall, from the tropical easterly jet, a little lower. And so when you have a westerly phase of a QBO, it tends to go right through the easterly part, so it looks a little messy like this. But if I go back to 21, this year again, we got a very robust, it's more robust than it needs to be because I'm using 9 meters per second now. If I go back to my 15 meters per second, there it is. So this is a QBO from this year. Now, I point this out because I'm not sure, I don't know if anybody's ever researched it, but what is the relationship between this QBO and these jet streams? And when the jet streams, when the polar night jet weakens and so on. Both of these circulations are at a similar elevation, although I think the polar night jet might be a little lower. Yeah, you can see here from the side that QBO is up there very high in the stratosphere, not really doing anything until above 20 kilometers, but the polar night jet is brought down to somewhat lower elevations. So there's some kind of a relationship there that I'm not sure about. One other thing while I'm in here I wanted to point out was the Walker circulation. And I've talked about this before. When you're talking about El Nino southern oscillation, you talk about the Walker circulation, right? The Walker circulation is an east-west circulation through the depth of the troposphere that's a direct, well, I'm not sure it's even a direct circulation, but it is an east-west circulation. And you can see it by looking at the velocity potential field called chi. And I do a chi in here. I put that on my page as well. And I have a chi and the height field looks like this. So this is how the Walker circulation would look in different years. This is a pretty, well, this is actually fairly atypical here. This is the 2016 Walker circulation. The blue is negative chi, which suggests convergence. Now this would be, let's get it up at a proper level. Well, this is at 356 Kelvin, I believe, is where I'm doing this. So this means that there's a net convergence or divergence of flow at 356 Kelvin. And in the other areas where there's red, that means the flow is convergent. And so if that's true, and this is in the upper atmosphere at 356 Kelvin, top of the troposphere, what you can imagine is going on is that air is rising under this blue to create divergence aloft, and air is sinking under the redder areas. So this is a kind of a wave number one, zonal circulation, air rising here and sinking everywhere else. And this is typical in the atmosphere. Now, in an El Nino year, I don't know if this was an El Nino year, but it looks like it is. In an El Nino year, this pattern is shifted over. Normally, this blue pattern would be shifted more toward the maritime continent from about India to over here. Let's see what it looks like this year. It might be more typical. Yeah, it's a little bit. It's mostly over here. Let's step through the years. Back to 16, 17, 18. Now 18 is really shifted over. 19, it's back. This is pretty normal. And 20, still a little shifted toward the east a bit. And back to this year. Now, the El Nino and southern El Nino occurs when you have a warm Pacific Ocean, and that seems to be a warm Pacific Ocean, particularly in the eastern Pacific, and that seems to be associated with this Walker circulation. So what we have is the El Nino Southern Oscillation, which is called ENSO for short, and it's the combination of the Southern Oscillation and the El Nino that we're talking about. Now, during an El Nino, when the Pacific is warm, we expect this east-west circulation to be shifted to the west. So as I saw in a couple of these plots here, like this case here, this looks like an El Nino here, in which case we'd have a southern oscillation index, which is shifted over to the mid-Pacific, where it's rising in the mid-Pacific instead of the eastern Pacific. And in a La Nina year, like we're moving into this year, we still haven't fully reached the La Nina. It shifted more toward the western Pacific, or at least in its normal case, it would be stronger. It's not particularly stronger today, but if I averaged this over a few days, it would look much stronger. So the El Nino Southern Oscillation is a combination of this east-west or zonal atmospheric overturning circulation matched with the Pacific temperatures. And again, when it's warm in the eastern Pacific during El Nino years, the tropical eastern Pacific, equatorial even more precise, when it's warmer in the equatorial eastern Pacific, we tend to shift this rising motion more toward the east. Now, this rising motion is important, and particularly the rising motion and the sinking motion is important because these motions superimposed on tropical circulations inhibit or enhance the formation of tropical overturning, such as convection or tropical cyclones. When you're in the blue area, here where the air is overall rising in this southern oscillation, or this Walker circulation, the air is rising overall, that's conducive to the formation of tropical cyclones, it appears. I mean, that's what the data tends to show. And when you're in the red area, it tends to suppress the formation of tropical cyclones. So today, it's not doing much of either in the Western Hemisphere. This is actually pretty unusual today. But that's all I'm going to say on that. One more thing I'll point out before I stop here is the relationship between the speed, the jet streams, speed back up. Just don't want to color this. Color the speed. And at the same time, I want to put on the column moisture, integrated column moisture, precipitable water, DBI. Okay, so there's the precipitable water, there's the jet streams. And here, what's interesting about the precipitable water is you can see all the various atmospheric rivers around the world. If I reverse it, then I get better content resolution. So this is for first year. Here's 16, and if I step through the years, I can see different cases of atmospheric rivers. Now, this big thing down here in the south, southern hemisphere, is not necessarily an atmospheric river. This is, I think, the southern ITCZ, which tends to split into two ITCZs in the Pacific. But these features like this that are coming down here, this is an atmospheric river coming down through Brazil, atmospheric river coming up here. This is what we had last week. And these atmospheric rivers tend to be associated with anomalies in the jet stream flow. And I can't really animate through this very well because it's different years. But you can see how it varies from one year to the other. We get many of these atmospheric rivers. And the atmospheric rivers, I think when I define an atmospheric river, I would define it as coming as a river of moisture that is rooted in the ITCZ, which is this band down here. Well, last week, when we had that big atmospheric river, it wasn't rooted in the ITCZ. It was rooted further north. It may have been rooted in the ITCZ way back here in the Western Pacific, but the atmospheric river last week that hit the West Coast was much further north. So that was kind of a strange one as far as I was concerned. But I'd have to go through another lecture to look at all the anomalies that were associated with that. So I'll stop here and let somebody else do it. Are there any questions about it? Anything else you wanted to see? Yeah, it's unfortunate that I lost my, what I stored, but.
Sure. I'll be quick. I need to log in, but nothing, Zoe just gonna log in. There's something weird with the AOS account on here. It's trying to follow a language that I don't understand, so. Yeah. We want to freeze it? Yeah. Yep. Well, we can't, I guess it's on for this.
All right, so I was snooping through satellite imagery yesterday and found some cool things. The first one, there's northeasterly flow through the St. Lawrence Seaway. Hopefully this diff will load. I thought that was absolutely beautiful. Just a river effect sort of situation over the entire St. Lawrence. And I don't believe that radar was really able to pick it up because the cloud tops were not particularly high, very warm. But generally speaking, the St. Lawrence Seaway and the eastern part of Lake Ontario is still 60 degrees Fahrenheit, and the air temps were like 45 at the surface. So not difficult to get something like this to happen.
But you wouldn't call that, that's not really a river, that's lake effect.
Yeah, I agree.
Yeah.
Yeah, I mean, once, you can see the flow bending along the sort of the valley, so you can more or less have a parcel of air stay over the river all the way from the mouth. So I thought that was pretty impressive.
What's one of the interesting things on there is Lake Ontario.
Mm-hmm.
And Lake Ontario, you can see it begin with a lot of wind parallel bands, wind parallel overturning, or I'm trying to say mesoscale
Yeah, that's the
cellular
uncommon
convection.
fetch for that.
But then it focuses into a single band on the downwind side of the lake. You can see that, and that is what we call a shore parallel band that's associated with land breezes from the two long axis shores. And so on the very western side of that Lake Ontario, you're seeing that concentrated band, and that tends to be deeper and probably causing some kind of precipitation on that lee shore. This is where we get very heavy precipitation, like you always hear about the Buffalo storms and things like this. But this is unusual in that this is a lake effect from the east, from the east northeast wind, and so normally we think of lake effects with a westerly component, but it can happen from the east. We get them in Lake Michigan a lot. But I think that's pretty interesting how you could see this concentration and collapsing into a shore parallel band.
Yeah, and I mean, typically, the shore parallel bands on Lake Ontario, they have a preferred side due to the convergence on one of the shores. In westerly flow, the convergent shore is typically the southern shore, but now flow is reversed, so the northern shore would be preferred.
Well, I think it's the reason it's on the southern shore is because it's normally a northwesterly wind or wind with a northerly component. Also, the lake is in that direction, right? So it's not, the winds, if you just had a straight easterly wind, that would prefer the northern shore because the lake is oriented northeast to southwest. If it's moving along the axis, so, yeah, I think that's part of it, but, it's still being driven by northerly cold air from the north. And, I would guess the cold air is really being advected from the northeast in this case, parallel to the lake.
You can also see some really nice valley fog dissipating with the heat of southern New York.
And tons of gravity waves in the northeast, short wavelength gravity waves.
You say that this part of New York is actually higher terrain with the Catskills over in the. Kind of cool, and I grabbed a sounding from this as well. Just from the initialization of the raft, and I grabbed it right inside the St. Lawrence Seaway, and you can just see that there's this very, very small, roughly dry adiabatic and very moist layer at the bottom. And typically for the lake effect, like to see very little directional shear in the boundary layer. I mean, I would agree with the idea that the band is becoming a shore parallel band, but I don't think it's land breeze if you have that much of a synoptic gradient wind.
But you wouldn't see it in the sounding because land breeze is something that develops in a diurnal part of the circulation. It's kicked up during the day, or it's kicked up relative to the lake. So where is this sounding?
Well, this sounding is in the middle of the St. Lawrence, so I've taken the sounding like right here.
Yeah, you wouldn't see it there. The land breeze is going to be relative to Lake Ontario.
Right, but don't you think a land breeze wouldn't form if you have over 10 knots of low level flow?
The land breeze in this case is cold. The land breeze is cold air from the land. I'm thinking is this visible?
Yeah, this is a visible satellite.
Yeah, so I don't know why the land, well, I guess the land would be cold because we're in a cold air mass at this point. But normally when you see that happening, the land is cold, it's in the winter time. The land is cold and the lake is relatively warm. Or maybe later November, when the land has cooled, but the lake is still warm, then you get a land breeze. So it's a temperature differential. You're not getting any temperature differential up in the lake, up in the St. Lawrence there, because it's not big enough water body to
But
start a land breeze.
on a summer day, a sea breeze doesn't fill if you have 10 knots of synoptic flow. So why
Yeah.
would a land breeze, which is
In the summer you'd have that. What is this day though?
Well, this is yesterday. I'm just pointing out that if you have such strong synoptic flow, I don't think a land breeze can fill.
It's going to overwhelm any of the.
It would overwhelm the circulation
from the land sea breeze.
So I think the shore parallel band aspect is purely just cold air, cold windy air flowing over warm water.
Then why is it focusing into a single band and wiping out the wind parallel bands in the upstream part of the
Well,
lake?
wind parallel bands prefer the short fetch of the lake, so once you've
They don't
taken
care.
partial
They're just
overwhelm
local. The wind parallel bands are a simple boundary layer phenomenon.
Right, but you would, if you had northerly flow over Lake Ontario, you'd never see a short parallel band. You'd always see wind parallel rolls. So I'm just saying that we have easterly flow, quite strong easterly flow over the lake, and I wouldn't attribute that to a land breeze. I would just attribute that to formation of a short parallel band in the windy.
Well, we'll talk about it later.
Sure.
Is it possible that it's an aggregate of the latent heating that's forming convergence down the middle of the lake as you get farther down?
Yes.
That's what I'm thinking.
That's what I would think.
It's the lake heating the air relative to the land that's cold, and then that thermal differential is creating
The circulation like this.
direct circulation over the lake. The air's rising over the lake, and that's overwhelming the effect of the individual wind parallel bands.
Agreed.
It's a really cool animation though.
Yeah, it is.
So yeah, that was one I thought was pretty cool. Another one, I was looking over the North Atlantic yesterday, we sort of situate ourselves. Let's see if I can. So just situating ourselves. There's our cyclone off the east coast yesterday, and I found this sort of suspicious looking little cloud layer in the open solid cumulus. This stuck out to me that it looked stronger than everywhere else in that little area, and I lined it up with the I think it's the 14 degrees Celsius isotherm from the North Atlantic current, and it lines up quite nicely. So you can see this enhancement of the cumulus right along the sort of the leading edge of the warm SSTs. And I tried to overlay the satellite imagery with sort of a color fill of the SSTs. And you can see right where the sea surface temperatures are at their maximum in the North Atlantic current. I have an enhancement of my cumulus right there. And I zoomed in on it a little bit down here. Try to convince everyone that those seem coincident at least. So I just thought that was pretty cool. I'm not sure I have anything else to say about it.
Sweet.
Cool.
All right, thank you.
So you want to take it away?
If anybody else ever just sees anything interesting during the week and wants to share it, this is, this is not the Michael Morgan show. This is open to anybody. So if you come up with something, just let us know. Bring it in. Thanks, Ian.
So I'll just wrap up looking a little bit at the satellite image. I think the first tab is the week long, and then talk about some of the future forecast. So this is the week long satellite imagery across Conus, North America. So that's the atmospheric river bomb cyclone event that Professor Morgan talked about last week that had substantial impacts on the West Coast, lots of rain, some power outages across both California, Oregon, and Washington. I think the lowest buoy measured around 942 millibars, so pretty intense cyclone, to say the least. We also had the emergence, Friday we didn't talk about it, but Hurricane Rook developed to a Cat 2 and made landfall in Mexico. And then over the week, making its biggest impact on Wednesday morning was another, it just barely missed the bomb cyclone criteria on the west coast here. Did you see storm? Nope, it was that one.
You want to
But
pick it up?
yeah, we'll come back. Yeah, Wednesday, another intense mid-latitude cyclone that was accompanied by strong moisture plume from the tropics, deep in 23 millibars in 24 hours, and it had, again, here, substantial impacts on the East Coast. Bomb cyclones are considered 24 millibars in 24 hours, so I just barely missed that rate. Still impressive event, and then obviously we've been hit with still present mid-latitude cyclone that's now beginning to weaken as it goes westward. Yeah.
There's just some amazing difluence almost right over us right at the end of this loop. From around that cyclone, the air comes up and just splits, starting
Yeah.
right kind of there. See how that's just
Yeah.
splitting north and south? It's crazy.
Yeah, it's definitely an interesting pattern that I don't know how typical it is. You can see, and you can come out of this and jump to the radar, at least some of the last. There's different versions of it, but so there's a data issue. I think we mentioned that earlier. So we lost a few hours this morning of data. Yeah, here's the precipitation associated with that cyclone. We got some trailing ahead of a now included cyclone. You guys see that precipitation pattern isn't visible here, but the cyclone is expected to weaken as it propagates east. There is some interactions possibly that could have intensify or lift in some ascent. There's some marginal severe weather risk, slight in on the east coast. Yeah, so as the system goes off, expect to see a little bit drier conditions for this upcoming week. Satellite. And based on both the issues with data and due to time, we'll just jump, I think, to, I'll show back to these maps. Let's start with Conus. So slightly different maps, but I thought they'd be good kind of synopsis. So this is showing the 250 hectopascal jet stream and the fill, the thickness in the red and blue. So the 540 line is usually where just denote freezing or not. Gives us thermal structure of the atmosphere, and then the sea level pressure in the black contours. So this is right about now, or 7 o'clock this morning. Again, that cyclone associated with the precipitation we got. I think it's the arrow key. If you go back, yeah, two steps. So earlier today, when Pete was pointing out that diaphragm region, I guess maybe it's associated with this very long, elongated trough, that there's precipitation, or at least a very large cloud head associated with this low that's stretched very meridionally. I don't know how common. The variable, if you click that and go down to precipitation, the last one. Yeah, so there's this very meridional precipitation band across pretty much the entire continental U.S. Do you have a good reason
so
for that?
if you go to the variable, you should be able to get like 250 millibar, 300 millibar irrotational winds.
Yeah, second one now.
So the point out here is Pete's sort of split. If you go forward in time slightly, you'll eventually see a flare up there. Go back one more, Pete, two more. You see sort of the flare up there of the irrotational wind at the peak of that cloud head. That irrotational wind should be able to act on those isotropes and complete the cutoff structure of the storm in this case. You've got almost a shear line to the north of the low structure, and then you've got the cloud head, strong irrotational winds, and you can immediately snap off the tip of that elongated trough in combination with a little bit of latent heat release, and you've got a nice cutoff cyclone over the lower Midwest. So if you go like two more in time, Pete, I think the thing will roll up quite nicely right there, and then that trough atop splits off, still part of the jet stream, and it still has a strong eastward propagated component, but our lower cutoff is almost dominated by planetary vorticity vection. So in the QG high tendency equation, it wants to propagate westward just as much as it wants to propagate eastward, and it's going to slow down considerably through, I guess, last night.
It's a good explanation for it. Yeah, that's what we're seeing here with this cyclone. We go back to let's go to the precipitation. So again, we're now in time and space. If we step forward, we'll see that after this cyclone moves off of continental U.S., we're going to head into a relatively inactive period. Going forward, so this is Sunday, as the cyclone looks like it might bring some more heavy precipitation to the east coast. See the cold front associated with that precipitation and the cyclone center. Other than that, the continental U.S. is going to get a bit more or less boring in weather. It does look like we might start getting a cold surge. You can see this 540, I guess in this case, this is surface temperature, or 800. What?
The blue is 0 degrees at 850.
Yeah, so we're starting to see freezing line pop up and some early trends from the north. So expecting some cold air advection, cool things up. If we go forward another 3 clicks, sure. So this is
1 p.m. on Sunday.
yeah. Sunday, again, still looks like we are going to start cooling down as we continue to get that cold air advection from the north. Over the continental U.S., relatively calm. You can, though, start seeing something emerging on the west coast, and that's what I'm going to spend a little bit of time talking about. So if you go back to the domain on the top, it says Conus. Switch to North Pacific. So if you then click on the Sunday, or the valid time, let's go back to, actually negative, let's go to Wednesday. So the west coast looks like it's going to get another relatively strong cyclone making landfall there, and it actually has some tropical roots to it. Let's switch the variable again from precip to, the top one. So this is a typhoon Malo that's currently dying off. It was a category 2 at one point, but it's dying off as a tropical system in the West Pacific, and is going to interact with and get absorbed by make an extratropical transition and make landfall on the west coast. So if we step forward a day, or we can just keep stretching forward, we see it interacting, and I'd say amplifying this jet streak probably from the outflow of the TC. We see it getting absorbed and making an extratropical transition. We're now, if you stop it here, you can see a nice frontal structure, cold and warm fronts associated with still a pretty intense cyclone, and associated also with some strong jet streaks. You can keep going forward. We are now back into a forecast space, 0Z on the 31st, so Sunday, Saturday evening, or afternoon in the Pacific. But we see this continuing to develop and have a pretty strong varicosity associated with it. Go forward. See that structure continue, and it makes landfall then about weather watch time, Wednesday. We're going to start to see some landfall on the 3rd. So something to take note of if you go to variable, and go down to the 700 hectopascal geopotential height and integrated water, IVT. So IVT is integrated water vapor transport. That can be an indication. Strong moisture transport, basically. So you can see again that there's this large moisture transport onto the East Coast, fully continuing. It's in the Gulf of Alaska, the main cyclone center, but possibly bringing some more precipitation to the West Coast that's still needed. The last week's storm definitely brought some much needed rain and snowpack to the severe drought they've been experiencing, but this storm could bring some more moisture in. So that is something that I found interesting as a tropical person, seeing how the tropics interact with the mid-latitude system. So yeah, you can definitely see some of this really high water vapor content. Integrated water vapor transport is likely due to the tropical beginnings of this storm. Yeah, we're starting to get into an active North Pacific cyclone time, so I'm sure at one point Professor Martin will also come and talk about his favorite West Coast storms. That is about all I had really thought of. If there's anything else anyone else wants to look at, we can also look a little bit more closely at Madison's weekend forecast. Or
For
space
those who
weather.
don't know, there was a big solar flare yesterday morning that could produce northern lights around here tonight and tomorrow night, depending on the forecast and how it ends up impacting the magnetic field.
Can you go to Pivotal and look at the, whatever it is, the last winter weather, the total accumulated snow and the last thing, what's gonna happen over the next 2 weeks?
You want the Mickey Mouse
384,
forecast?
yeah, and go the winter weather down there.
This is the fantasy forecast.
Yeah, it's a fantasy. Total accumulated snowfall.
Yeah.
Looks like we won't be getting snow yet on this singular forecast, 384 hours out, which is a very valid time to look. But
Check
yeah,
some other model runs too.
we could compare some. I don't think anything else can't quite look at this date. So
Yeah, this is, I think, the one I was looking at before, the 6Z one.
6Z looks like we've gotten a trace amount of snow, or about an inch. Can you hover over that?
A little bit.
Yeah, we've got Madison, according to the 6Z run, has about a trace to an inch of snow, depending on how you hover,
At the end of that period, but when
at
did
the end
it,
of that period.
whenever it fell, I don't know.
According to the 0Z run, we have gotten 16 inches of snow.
That's still snow?
It's
Yeah,
accumulated snow.
holy mackerel.
Which is exciting
Yeah.
and terrifying, November 14th.
Previous
But
one.
that signal is not present. Granted, I think we're switching around times a little bit because we're looking at the last forecast hour. But still, that doesn't seem to hold in many
What-
forecasts.
You can space through that, you know, Pete, what you do is you
Yeah.
do the animation and then use the cursor.
If
Go to
we-
forecast loop. And then use the cursor to go back and forth over that bar up there, the time bar. Yeah, just pull that back and forth and you can look at where the snow is coming. So you want to put it back on that other
I was gonna
day.
say,
Zero
I think
Z?
it's the
You want-
0Z run that gave us a nice November snow.
Yeah, now pull the bar over there and see where that's coming from.
earthquakes.
Ooh.
2 of them.
Around the November 7th and 8th, we get a nice
Wow.
snowstorm,
270.
which could be exciting.
So,
I'm curious between the runs whether or not the amount of snow accumulated is the storm system track is changing or whether the temperature is changing.
Yeah.
Something cool in that one was you see the lower Lake Michigan still so warm that it gets protected. All of Chicago area gets protected from that.
I'll go back to the previous one.
I think it's also interesting that all my summertime annual plants, that are basically tropical plants, are still alive. We haven't had a killing frost, and I know some TV meteorologists are saying, oh, that was a killing frost last week, but it wasn't. It didn't kill anything.
No, it just got cold at the
Yeah.
airport.
Yeah.
Airport's in a bowl. If it's clear and calm, it'll get colder at the airport.
And I think we're gonna make it to November 1st, and they're still gonna be alive.
I would agree.
And that's really unusual.
Yeah.
Mm.
Yeah, you can definitely see the lake effect warming and being.
I'm still waiting for my leaves to fall in the yard, you know, it's because I gotta go out there and mow them and rake them up, and there's nothing down there. All the trees are still green in my yard. And how unusual is that? We're heading into November now.
Are you looking at the climate?
Yeah, I was gonna look at, Ed said he updated.
Is there still corn on the farm fields?
No, I don't think that's, that's more of a light thing, but.
So this is the yearly average high and low temperatures in Madison, and then 2021's data. We have been on the higher, warmer part for this, basically the beginning of the semester. We've been enormously warm, but it looks like we've gone back down to pretty average. There are low temperatures. We've had a few nights, as probably all experienced, dipping below the freezing line, but yeah, we haven't had that extreme. Is 2020 on here? Can we
Yes.
scroll down to see the difference? So we're about here. We definitely had some cooler days earlier on, much farther below the freezing temperature, which I recall also. Yeah. 2020.
But the difference seems to be the variability, that we're not shooting really cold at any time. We're not getting super warm, but we're not getting super cold.
Yeah.
So, yeah, I think the average first frost is October 1st, for the first frost, not the killing frost.
Yeah. Sounds right.
But I think we're well past a couple of weeks after the average first killing frost,
Yeah.
which is a little unusual.
I mean, 2 years ago, in 2019, we had, what, like 10 inches of snow?
For Halloween.
Yeah. If you scroll down, we can also look at where we are. We're still a little bit below average, but pretty average for cumulative precipitation.
Still on last year's snow, that update that.
Yeah. Last year, we ended the precipitation year at a deficit, so looks like we're staying drier, which with La Nina, I believe we're supposed to have a slightly cooler and drier winter.
La Nina, yeah, it should,
And then,
it's kind of normal. Now, La Nina is like a normal year where the Pacific is cool in the east,
yeah,
but it's cooler than it normally would be. So it's like super normal, is what La Nina is. And so, I mean, in a La Nina year, if we're in a cold climate area, we tend to be a little colder
yeah,
in cold outbreaks. But there's not a lot of variability. Like in El Nino years, you get a stronger subtropical jet, so there's more on, off all winter long. And you may stay a little warmer on average. In a La Nina year, you tend to just stay persistent and not get a lot of anything. That seems to be what's actually happening right now, come to think of it.
well, that is about it for today.
Thank you, everyone, for presenting. If you see something interesting during the week, save it and let me know, and we'll get you up here.
You want to see about changes?
Oh, yeah, we could do that.